Hi, and welcome back to another episode in the C# Practical Funkiness series. In today's episode, we're diving into a simple but powerful technique known as memoization. Memoization helps us speed up expensive or repetitive function calls by caching results we've already computed. This is especially useful in recursive algorithms where the same inputs show up over and over. A classic example is the Fibonacci sequence. In its naive recursive form, it recalculates the same values repeatedly. For example, calculating Fibonacci 100 using basic recursion on a typical PC would take approximately 72,000 years. That's because it's solving the same subproblems again and again, and that's where memoization comes in to help. With memoization, we solve each unique subproblem only once and store the result. Then when that same input shows up again, we return the cached answer instead of recalculating it. This transforms exponential time problems into something much faster, often linear time. Let's look at the Fibonacci slow method. This is the naive implementation. Line 18 defines the method. Line 20 handles the base case, and line 21 is where the real trouble lies. It recursively calls the function twice, which results in an explosion of duplicate work as the value increases. On line 26, we use this local method to calculate the Fibonacci value for position 40. As a side note, on my PC, I would not go beyond 45. As the time rapidly increases, and I mean at a ridiculous rate. As I was curious, I asked an AI how long it would take to calculate Fibonacci 200 on a standard PC. It didn't laugh, but he stated that it would take more time than the universe has existed, stating the universe has been in existence for 13.8 billion years, and Fibonacci 200 would take that multiplied by 10 to the power of 30. On line 30, we just print out the results. Now let's restructure the routine slightly so we can use a memoize method that I added in a utility class. We will see this in a minute. On line 34, we declare the memoized Fibonacci delegate before it's instantiated, as we need to reference it inside its own definition when passing it into the memoize method. We restructure the function so it can accept a delegate which allows us to inject a memoized version of itself, and given the size of the number we are calculating, we need to use the big integer type to store the result. On line 44, we use our memoize method to wrap our function. And just like that, we cache every intermediate result. And on line 46, we ask for the Fibonacci value for position 200. Let's run the code and pray it works, as otherwise we could be sitting here for a very long time. So just over 1 second for the Fibonacci value at position 40 using the naive recursion method, and just over 16 milliseconds for the value at position 200 with a very big number for the memoized version. Now, to be honest, most of the applications that I build don't rely on heavy mathematical algorithms like Fibonacci or other problems with overlapping subproblems. These types of challenges are more common in academic settings or specialized domains like scientific computing or dynamic programming. That said, there are still very practical use cases for memoization in everyday development. One area I found it especially helpful is in serverless architectures like Azure Functions, where state is short-lived and you're trying to reduce redundant computation or avoid unnecessary external calls. It's also handy when I'm working on personal projects that consume free APIs, which often come with rate limits or quota caps. In those scenarios, a lightweight memoization utility like the one I'm about to show you can help avoid repeated API calls without having to pull in a full-blown caching library or external dependencies. It's a simple and reusable pattern that gives you a layer of in-memory caching even in stateless or constrained environments. The Memoizutils class contains two utility methods, one for synchronous and one for asynchronous memoization. These are identical other than the awaits. These methods are based on the code that I frequently use in caching services for multi-threaded applications. The approach uses a simple lock manager implemented with Semaphore Slim to ensure thread safety on a per cache key basis. This helps maintain performance and throughput, especially under high contention for specific keys. Unlike full-featured caching libraries like Microsoft's Memory Cache, which supports eviction and expiration policies, this utility opts for a lightweight, time-based expiration model. You can easily modify this to use a call count or other strategy if that better suits your scenario. The design relies on closures to encapsulate two concurrent dictionary instances, one for storing the cache values and another for managing semaphores, locks, per key. The logic is straightforward. If the value exists in the cache and hasn't expired, it's returned immediately. If not, access is gated using a semaphore. The function is executed, the result is cached along with a new expiration timestamp, and then it's returned. This implementation has been adequate for my needs, but you can certainly extend it further, for example by implementing cache eviction once a threshold is reached or integrating diagnostics. Please note, this solution assumes the T1 argument type provides the appropriate uniqueness given it's used as the cache key. Okay, let's look at another example that's not some mathematical algorithm. In this demo, we're going to use our Memoization utility in a more practical real-world scenario, calling a free weather API that has a rate limit of 600 calls per minute. To keep things simple, I'm not using the HTTP client factory, though you should definitely use it in production. We define three URLs for London, Paris and New York, and then use our Memoization utility Memoiz function to wrap the getCurrentWeather method. This means that once we fetch the weather for a city, we cache the result for a short time, in this case 2 minutes, so repeated requests don't hit the API again. On line 31 we use enumerable.range to create 600 weather request tasks, 200 for each of the 3 cities, the maximum allowed per minute, and on line 36 await the results. After this we then retrieve the weather one last time for each city. These should come directly from the cache as well. Without memoization, this would exceed the rate cap and start returning errors, but with memoization only the first call per city goes over the internet, the rest are served from memory instantly. Finally we print the results and show the total time for all 603 calls, only 3 of which actually hit the internet. Memoization handled the rest. Right, let's run the app and view the results. 603 function calls with 3 trips across the internet took just over half a second, but importantly no limits were exceeded. Before I wrap up for today, if you watched the earlier video on partial application, this is a perfect example. You can bind a specific HTTP client to the weather function using partial application and then memoize that new function. The function on line 67 allows you to do that with the commented out code showing example usage. I hope you found something of interest in this video, and as always feel free to leave good or bad comments and I'll do my best to answer any questions raised. If you found this episode or source code helpful, please consider liking and subscribing to help support the channel. Thanks for watching, until next time, bye for now.